Okay, so this is an example of talking about the domain of a function g of x and the range of g of x and comparing it to the domain and range of the inverse function given the function is 1 to 1. So since we know the function is 1 to 1, since we know the function is 1 to 1, we also know that g inverse of x is a function, meaning it passes the vertical line test. So in this circumstance, we can make a relationship that if we have g of x and its domain and its range, we know this compares to the inverse function g inverse such that the domain will correspond to the values of the range and the range correspond to the values of the inverse's domain. So in this circumstance, I'll do it in red, that the domain of g is x such that x is greater than -3 and x cannot equal to 0. So we're going to have x such that x is greater than -3 and x cannot equal to 0. And then the range is y such that y is less than or equal. Actually, I'll do this one in a different color. I'll do this one in green. So this one is going to be y such that y is less than or equal to -7 all over 2. So this will be the domain of g and the range of g. Now we have to determine the domain and range of g inverse. So we recognize that the range of g corresponds directly to the domain of g inverse. So we can write the domain of g inverse as x such that x is less than or equal to -7/2. And in this circumstance, the domain of g corresponds to the range of g inverse. So we can write this as y such that y is greater than -3 and y cannot equal to 0. So this is just a nice easy way of determining domains and ranges of an inverse function given the fact that we know our function is 1 to 1. So now we are going to evaluate a logarithmic function, or a logarithmic, I guess we can say a logarithmic, it's not an equation, it's a, I guess, it's just a logarithmic identity, or a logarithmic, yeah, just a logarithmic identity. So not even a logarithmic identity. We could call this, I guess we could actually call this a logarithmic expression. So it's not an identity, it's not an equation, there's no equal sign. So this is just a logarithmic expression. So here we recognize that we have our log and log base x of 2, log base x of 3, and log base x of 5. So, excuse me, we're going to have to transform this into log base x's of 2s, log base x's of 3s, and log base x's of 5s. So if we have log base x of 144 x squared all over 25. I can rewrite this as the multiple of 144x squared, so we can add these two logs, and then we're going to subtract the 25 at the end. So I'm going to have log base x of 144 plus, because I'm multiplying between these two, log base x of x squared. And then because I'm dividing, I can subtract out log base x of 25. So now to make it easier on myself, I'm going to break down 144 using a factor tree, one of our famous factor trees. I know this will break down to 12 times 12. This breaks down into 3 times 2 times 2, and this breaks down to 3 times 2 times 2. 3 times 2 is 6, times 2 is 12. So again, these are my prime factorizations. So this is really going to be 2 times 2 times 2 times 2, which is 2 to the 4th times 3 squared. So my prime factorization of 144 is 2 to the 4th times 3 squared. So here I can split this up, or I'm actually just going to rewrite it at the beginning. Log base x of 2 to the 4th times 3 squared. Notice I'm multiplying my arguments, so I can split them up as the sum of two logs. This will still be plus. I'm going to go ahead now and I'm going to bring this coefficient out as a, I'm going to bring this exponent out as a coefficient. So I'm going to have log base x of x, and I'm going to rewrite 25 in terms of log base x of 5 squared. So I hope some of you now are recognizing at this point log base x of x is equal to a value of 1. So I'm sure that's screaming to us. So now I'm going to split up this first log into log base x of 2 to the 4th plus log base x of 3 squared. I can split up my log because I'm multiplying the arguments. And again, if you're not familiar with this identity, make sure to research logarithmic properties so that way you can recognize the identity. So now we're going to still have 2 times the value of not log base x of x. I'm going to say this is 2 times 1 because I know this to go to a value of 1. And I'm going to bring this exponent of 2 out as a constant coefficient. So I'm going to say this is minus 2 log base x of 5. So notice I have my first value of log base x of 5 found. So I'm just going to go ahead. I'm going to identify that in terms of blue. I don't have to work with this guy anymore or mess with him anymore. So now this will equal to, I'm going to bring my 4 exponent out as a coefficient. So I'm going to have 4 log base x of 2. Notice log base x of 2 again, plus 2 log base x of 3. And I'm happy with that. 2 times 1 just gives me a value of 2, minus 2 times log base x of 5. So notice here, I know log base x of 2 is equal to 0.05. I know log base x of 3 is equal to 0.25. And log base x of 5 is equal to 0.1. I can go ahead and substitute those values in. So I will have this being equal to 4 times log base x of 2, which is equal to 0.05, plus 2 times log base x of 3 is 0.25. Still plus 2, I can't forget this plus 2 which came from this, minus 2 times log base x of 5, which is 0.1. 4 nickels, or 4 times 0.05, gives you 20 cents. Plus 2 quarters will give you a value of 50 cents. Plus $2, minus 2 dimes, which is 20 cents. So my 20 cents cancels, and I'm left with 2 plus 50.50, which gives me $2.50 or 2.50. I was using the money analogy because it tends to be a little bit easier to work with, and I enjoy doing that. So that's going to equal to 2.50 or 2.5. So this is just a way of us working with our logarithmic properties and doing a little bit of arithmetic at the end to demonstrate our strength of constitution of our logarithmic properties. So let us continue. So now we have to graph the function x squared, x plus 1 squared, and x plus 4. So first of all, I'm going to go ahead and I'm going to identify my y-axis, my vertical y-axis, and my horizontal x-axis. And I won't be able to draw this perfectly, and I guess I should be more specific in the instructions and say that this is not graph perfectly, but just graph an impression or give an idea of what this function will look like. Because here we're going to use our zero multiplicity theory. So we're going to use our zero multiplicity theory. So first thing, if I want to find my zeros, I set f of x equal to 0. So I'm going to have x squared times x plus 1 squared times x plus 4 equal to 0. Since I'm multiplying each one of these terms, I can set them all independently equal to 0. Solving now, I'm going to get x equals to 0. Here I would take the square root of both sides. Here I will take the square root of both sides and then subtract 1. So I get x equals to negative 1. And here I subtract 4 on both sides, so I would get x equals to negative 4. So these will be the zeros of my function. Do not confuse these with vertical asymptotes. These are my zeros. So I have a 0 at 0. I have another one. I'm going to spread this out just to make it easier on myself. I'm going to say this is negative 1. I'm going to say this is negative 4. It doesn't have to be perfect, just to identify where these zeros are. Hopefully we can see that. I'll do them in red actually so we can see them. So I have negative 4, and then I'm going to have negative 1 and then 0. So these are my zeros. Now I'm going to arrange these in a tabular format. So I have my 0 here, and I'm going to arrange them in ascending order. So I have negative 4, negative 1, and 0. Their multiplicities will be how many times they occur. Notice the multiplicity of my 0, 0, is in fact a 2, 2 which is even. My multiplicity of my negative 1 is in fact a 2, which we can see from the exponents. So that's also even. And then lastly, the multiplicity of my negative 4 is only a value of 1, which is odd. Therefore, now I can determine the action of the graph. Since it's even, this will only touch. This will also touch. And here it will cross at 0. So now I have an idea of what's going to happen to each one of these zeros. But we must identify the leading term analysis. Notice here we're going to have an x squared from the x squared. Here we're going to have another x squared. And then lastly, we're going to have an x. X squared times x gives me x to the fifth, a positive leading coefficient, which means we're going to start down here in quadrant 3, do something in the middle, and then go up. So now I know I start in quadrant 3, so I'm going to have to get a little closer. I'm going to start down here in quadrant 3, and then at -4, I am going to touch, and then I bounce back off. And then at -1, I touch again, and I bounce back off. And then at 0, I actually cross, and notice I extend all the way up into quadrant 1, which is what I expected to do based off of my leading term analysis. So again, this is not a perfect depiction of this function. However, we have our critical points being the zeros of the function, -4, -1, and 0, how it touches at -4, touches at -1, then crosses at 0, and we used our zero multiplicity to determine these values.